Hello everyone, welcome to lecture 3 of week 6 of the course Power Network Analysis, in which we continue our discussion on transmission line models and use of these models for performance assessment of transmission lines under different operating conditions. In today's discussion, we will specifically look at or talk about the long line model, which is the most precise, perfect, accurate model, if we were to say, compared to short line or medium line model, which we have discussed in the previous few set of lectures. So, compared to short line or medium line model, the long line model, it, as I mentioned, would be the best possible accurate representation of actual transmission line. So, let's see what this long line model looks like. In fact, short line model and medium line model, those models could also be replaced by long line model. The only word of caution is that the numbers or analysis that we would expect from a short line model, the same set of analysis or numbers would be also obtained if a short line was to be modeled as a long line, and hence there would be hardly any difference in terms of accuracy or the numbers that we would get. While on the other hand, for analyzing long line model, the time required may be higher or the complexity involved may be higher. So, a word of a trade-off is always desired for the computational complexity as well as the accuracy involved. So, that's the reason why we are segregating short line, medium line and long line models. So, long line model, if we talk about, it's pretty obvious that as the line length increases, the effect of total line capacitance and probably the conductance, if it can be modeled, it no more becomes negligible. The quantum of line capacitance or conductance becomes appreciable. And obviously, as line length increases, the line resistance and inductance aspect would also increase. And the ratio of capacitance, resistance and inductance, they would depend on what are the per unit line capacitance, resistance and inductance respectively. So, as a result of higher line capacitance, the associated line charging current or the capacitive current becomes significant or appreciable, specifically in long line model or in the medium line model, which regulates the flow of reactive power flow in the transmission line or transmission network and thereby affecting the related terminal voltages. And in long line model, the lumped representation would no more be applicable. Actual network parameters, they are physically distributed in nature. So, we would use the distributed network representation or distributed parameter representation in long line. So, typically the long line model would be applicable for lines of length beyond 250 kilometers and operating voltage above 400 kV line to line. Line capacitance, as I mentioned, is no more negligible. It has to be considered. Distributed line parameter representation is a must, no matter how small or large the line section is, if long line model is to be considered. And in this small section or large section, whatever section we take for the long line model, every section would have a series impedance thanks to line resistance and inductance, and the same section would also have a shunt admittance, which would represent what is the line capacitance and conductance, provided conductance is modeled properly. So, shunt admittance definitely would have line capacitance aspect. If conductance can be modeled, then conductance can also be considered in the long line model. And as a result, the resulting equations that we would observe, they would become no more algebraic, they would become differential equations. So, let's understand or see how do we get these differential equations instead of the beautiful, simple algebraic equations in short line or medium line model. So, what I have considered here is one such long line whose line length is LL kilometers. And since we are developing these models from single phase or per phase equivalent basis, so I can always correlate or define that the potentials at the sending end Vs and the receiving end Vr, these potentials or voltages are all being measured with respect to a reference. That reference could be the neutral or the ground point. So, in this two-port network representation, the terminals marked as negative, these are actually fictitious negative, they could be referred to as the fictitious neutral or ground from which receiving end voltage Vr and sending end voltage Vs are being measured. Similarly, Is and Ir, they are the respective per phase sending end currents and receiving end currents respectively. And each of this line section, every small, no matter how small or large the section is, each section of the line has a series impedance which is denoted by small z, in unit being ohm per kilometer, because the units that we have defined for R, L, the small r, small l, small c in the previous module, they were evaluated on a per unit length basis. The per unit length could be meter or kilometer, and that's the reason why Z, which is the per unit line series impedance, is ohm per kilometer as units. Similarly, small y represents the shunt admittance on a per kilometer basis, where it incorporates the effect of line capacitance, and if conductance can be modeled, then G would become non-zero in that case. And over here, omega, which is common in both small z and small y, this is equal to 2 pi f, where f is the source frequency at which the voltage source Vs and Vr are operating. And in this line's length of small ll length, we are choosing or we are measuring the distance or the length of this line from the sending end perspective. So x is that line length along which the measurements are being made or analysis is to be made. So for x is equal to 0, we would refer that our voltage and current, they would pertain to the sending end quantities. And when x becomes equal to LL, which is the actual line length, then we would get the currents and voltages which would refer to the receiving end quantity. Any value of x, again remaining positive, between 0 and LL would refer to the voltage and current at a distance x from the sending end. So that's the reason why line length, which is marked as x, is being measured from the sending end. And if we look at the boundary conditions which I have already explained, for x is equal to 0, V of x, which is the voltage at a distance x from the sending end, and the per phase current as I of x, which is the current at a distance x from the sending end. As per boundary conditions, when x becomes 0, V of x equal to 0 is nothing but sending end voltage, and I at x is equal to 0 is nothing but the sending end current. Similarly, we also have the boundary condition at the receiving end, which I mentioned that if x becomes equal to LL, then this voltage should refer to the receiving end voltage, and corresponding current should also refer to the receiving end current. So we have two set of boundary conditions, one for sending end and the other one is for the receiving end. Now if we apply or take a section of width delta x at a distance x from the sending end and mark two nodes which are nodes A and B. So if we apply KVL across nodes A and B, then by KVL we have node A voltage as V of x, which is written or marked over here. So V of x should be equal to the voltage at the node B, which is V of x plus delta x. And since we are flowing or going along the direction of flow of current, so the corresponding voltage drop that is observed is going to be equal to I of x into the impedance which is appearing is Z of delta x. So we have I of x, the current through this series impedance, multiplied by the actual impedance of that section. So remember, the unit of Z was ohm per kilometer. Delta x is also a distance. So when we multiply Z into delta x, that results into the overall series impedance of section delta x. Similarly, y into delta x would refer to the actual or total shunt impedance for the section of width delta x. So this is our KVL equation. One would also counter or say that, oh, why did I choose I of x? Because at the initial or starting point of node A, the current is I of x, whereas at node B, the current has now become I of x plus delta x. So yes, instead of current I of x, this term can also be written or replaced by I of x plus delta x. The overall resulting equation won't change drastically. Please remember, we are assuming delta x to be a very small section of the actual line length section. So if we apply KVL, we have this approximate equation where I of x could also be I of x plus delta x. The overall resulting equation won't change much. And if we now rearrange terms, we have v of x plus delta x minus vx equal to minus of z delta x by I of x, which we again, when divide and take the limit of delta x tending to 0, because remember we want to accurately model each minuscule line section. So that's why we are taking the limit of delta x tending to 0. So in that case, even if we had, let's say, instead of I of x, we had I of x plus delta x, then when we apply the limit of delta x tending to 0, I of x delta x, if it would have been placed over here, then for limit the I of x plus delta x tending to 0, it would eventually become I of x, and that was the reason why I mentioned that we could have I of x or I of x plus delta x in the current KVL equation. So if we take this limit, we have our first differential equation, first order differential equation, which says the first derivative of voltage from sending end with respect to the length or distance x should be equal to minus of z into I of x. Remember, z here is having a unit of ohm per kilometer. Similarly, if we make use of the KCL along node A, because you also have to consider the importance of the shunt admittance. Through KVL, we are considering the importance of presence of the series impedance. The shunt admittance aspect can be taken care of through the KCL philosophy. So if we apply KCL again at node A, we have, before node A, we have current I of x, and just after node A, we have current I of x plus delta x, and along y of delta x, there is a voltage appearing whose quantum is v of x. So the way we applied KCL for nominal pi model, T model, and medium line model, on similar lines, if we apply KCL, then the equation that we are expected to get by KCL at node A would approximately be equal to v of x into y of delta x plus I of x plus delta x. So now you may again question or think, oh, why did I choose v of x voltage? The logic remains the same. Even if you would have chosen v of x plus delta x instead of x, because delta x is tending to 0, the overall differential equation that we are likely to get won't change. So if we apply KCL at node A, we get our usual equation which I had written in the previous slide. We rearrange terms and take the limit of delta x tending to 0, because the line section has to be accurately modeled for every minuscule section. So we get our second differential equation, which says the first derivative of current from measured from the sending end with respect to the distance itself is equal to minus of y into v of x. Please note the unit of y here is sigma inverse per kilometer. So if we look at our overall governing equations, we have two first order equations, and these two first order equations, they can be again rewritten in terms of pure homogeneous forms. So we what we do is we take the further derivative, first derivative, or we take the derivative of this first equation, which results into d2v by dx square, which is nothing but minus z, because z is a constant. It doesn't depend on the line length. So I of x derivative comes into here. And again, if we substitute di by dx, which is nothing but minus of y vx, we get zy into vx. On similar lines, we have our second differential equation, which is purely in terms of currents. So if we compare these two equations, they are pure homogeneous second order differential equations. One entirely in terms of voltage, and the other is entirely in terms of currents. So both current and voltages equations that we saw over here, please remember that these voltages and currents are phasor quantities. They are in frequency domain, and hence if we have to find the solution of v of x and I of x in terms of x, we would still be getting voltage and current at a distance x, again in frequency domain and not in time domain. We'll see the impact of time domain modeling of long line model in the next lecture. So please have patience till that. So now, if you are wondering what is the solution form of these equations, again, as I mentioned, these are beautiful second order linear homogeneous equations. By linear, I mean that if I take a combination of signals or combination of phasors, individually if they satisfy these given differential equations, then the combination of these solutions would also satisfy these individual second order differential equations. So now if we are guessing what could be the standard solution form of these equations. So let's say we focus on the first equation, which says double derivative of voltage with respect to the distance is equal to Zy into V of x. Uh, through experience and mathematical basis or analysis, it is imperative that if we have V of x as an exponential function, let me write that exponential function as a1 into e to the power of gamma x, where I still don't know what are a1 and gamma. I've just taken a generic form of solution or general form of V of x, and I'm trying to understand or guess whether a exponential function can be a solution of this equation. So let's try that. In order to satisfy the corresponding equation, what I should do, I should first find what is the first derivative of voltage for the chosen analytical form. So a1 is a constant which is unknown, a1 remains same. E to the power gamma x derivative would be gamma into e to the power gamma x again. I take the second derivative, dv square by dx square. It would come as a1 is constant, gamma is also a constant which is not known, and hence I have gamma square e to the power gamma x. Now, if I put these numbers individually over here, I get that a1 gamma square e to the power gamma x should be equal to z of y a1 into e to the power gamma x. a1 is a constant which depends on the boundary conditions, and assuming that a1 is not 0, so essentially for the solution or for the equation to satisfy, we have the condition that gamma square is equal to z of y, which again can be written as gamma of root over of zy. Now, what do you expect the unit of gamma would be? That's the reason why I mentioned that the unit of gamma is ohm per kilometer. The unit of y is ohm inverse per kilometer. So if I multiply z of y, the overall unit of z of y is nothing but 1 by kilometer square. And that is the reason why gamma is root over of zy with unit of only kilometer inverse, because gamma is root over of zy, so the unit of this is 1 by kilometer only. Gamma is called as the propagation constant. On lines of a1 e to the power gamma x satisfying the voltage equation, we can also have another exponential form where e to the power minus gamma x comes in. So in a way, the general solution of first equation can be written in terms of two exponential sums, and a1 e to the power gamma x itself satisfies the solution. A2 into the e to the power minus gamma x also satisfies the first differential equation on lines similar to this. So their combination also satisfies the solution, and that's where these equations are linear. Gamma is root over of z of y, which is called as the propagation constant. Since z and y themselves are complex numbers, the square root of product of two complex numbers would also be a likely complex number, and that's the reason why gamma has a real part known as attenuation constant, and j beta, where j is root over of -1. Beta is called as the phase constant, units of radians per kilometer, and attenuation constant is Nepers per kilometer. Nepers and radians, as such, they are dimensionless quantities, so whether the units represent or not, it's not important. Just to segregate the real and imaginary part of propagation constant, these units of attenuation and phase constant come in. So if this is the general form equation of V of x, can we not also derive the general form of equation or solution for I of x? Yes. What we would do, we would go back to our actual equation, that if V of x is satisfying this particular general form of solution, then we can actually make use of this equation where a1 e to the power gamma x plus a2 e to the power minus gamma x is derivated once, and that same function is plugged in over here where we would get I of x. So if we do that, then as I mentioned, a1 and a2 are two conditions, constants will depend on the boundary conditions. And similarly, if we take the derivative, we can also get the closed form solution of I of x, where capital ZC is nothing but z by y, z by gamma actually, and Z, and it's called as characteristic impedance. Since it is the impedance, its unit is omega. How come ZC had a unit of omega? The overall analysis could be very well obtained from this resulting expression. So recollect, Z unit, a small z unit is omega per kilometer, Y unit is omega inverse per kilometer. So if I take z by y, its unit would be omega per kilometer divided by omega inverse per kilometer. Per kilometer gets cancelled and I have omega square. The square root of z by y will also have a root of omega square, which essentially leads to omega as a unit. And that's the reason why ZC is a characteristic impedance. It's unique for a given long line. The importance of characteristic impedance would become very obvious when we actually delve or go deep into the performance assessment of the line under different operating conditions, which has still time. We will probably discuss it in the next lecture. And as I mentioned, A1 and A2, they are constants, so they can be obtained using boundary conditions. Since we are measuring our voltage and currents from the sending end perspective, so we use our first boundary condition where at x is equal to 0, V is Vs, and at x is equal to 0, I is equal to Is. So if we put x is equal to 0 in both these equations and substitute V of x equal to 0 as Vs, I of x is equal to Is, what we get here is for x is equal to 0, this term becomes 1, this term becomes 1. So essentially I have a1 plus a2 is equal to V of s. Similarly, if I put x is equal to 0, this term becomes 1, this term becomes 1. So I have a2 minus a1 as I of s into zc. There are two simultaneous equations, two unknowns are there, Vs and Is, Zc, they are known. Vs and Is are known from the measurements perspective. Zc is a characteristic impedance which depends on the per unit series impedance and per unit shunt admittance. So if I solve these equations, it's pretty obvious that from here I can get A2 as Vs plus Is Zc by 2, and A1 would be V of s minus Is Zc by 2. So since Vs, Is, Zc, they are known, so in a way A1 and A2 are also known, and from these known A1, A2 values, we can substitute those constants which are now known in terms of V of x and I of x, and eventually we would get V of x as these expressions. These two expressions or terms, essentially the sum of the mean of e to the power gamma x and e to the power minus gamma x, mathematically it also resembles to cos hyperbolic functions. So the way we have sine cosine functions like cos of x, sine of x, on similar lines we have hyperbolic functions, cos hyperbolic x, sine hyperbolic x, and essentially cos hyperbolic x refers to a function of this order. So basically this term is nothing but cos hyperbolic of e to the power cos of gamma x, and the second term within the brackets is nothing but sine hyperbolic of gamma x. So that's where we get our hyperbolic functions. On similar lines, we can get our I of x in terms of sine hyperbolic and cos hyperbolic functions. V of x and I of x, now they are known in terms of Vs, Is, Zc, and depending on the line length x, we can figure out the actual voltage and current at any distance x from the line. One would wonder what was the complexity involved in this. The complexity involved in finding out the currents and voltages through the actual long line model expression is the effort needed in figuring out the hyperbolic cos functions or hyperbolic sine functions. Please remember, like cos hyperbolic and sine hyperbolic, if they can exist, then we can have other hyperbolic trigonometric functions possible. So tan hyperbolic, cosine, cosec hyperbolic, sec hyperbolic, they can all exist. The effort required is in finding out or evaluating those hyperbolic functions, whereas unlike in short line model, medium line model, we had just known constants. So that's the major computational complexity involved. We know V of x and I of x at a distance x from sending end. So at the receiving end, if we put x is equal to LL, we have VR and IR in terms of VS, IS, ZC and actual line length. Gamma again is root over of ZY, where small z and small y, they refer to per unit line series impedance and shunt admittance. In the next lecture, we will continue our discussion on long line model, and we would see some beauty behind the lossless condition, that if a transmission line is well designed and if it is long enough and operating at high voltages, then certain specific phenomena happens specifically for lossless condition, which actually becomes very useful to understand the cases where lightning, if lightning strikes, how would the voltage waveforms, current waveforms appear in a transmission network. The same analysis can also be used for doing fault analysis in DC networks. So essentially, the lossless long line model, it creates the premise for such discussions. Unfortunately, given the limited time that we have, we won't be able to discuss the lightning analysis and the fault analysis of DC networks, but they do arrive or come from the discussion on lossless long line model. Thank you.